All right. Okay, so again, little review from yesterday. We have our input-output machine here. Our input is the first number. This is our rule, and this is our output. So we're going to apply that to the others. So if our input is 0, I'm going to take 0 and divide by 2. If you remember from yesterday, we talked about zeros and division. You can always take a 0 and divide it by another number, and you get 0. 2 divided by 0 would be impossible, right? So you can always take 0 and divide another number and get 0. Add 1. So your output should be 1. The next one should have been simple. 2 divided by 2 is 1. 1 plus 1 is 2. The next one might have been a little tricky if your positive and negative practice is off, but you should have -3. If you did not get -3, make sure that you take a second and double check your work. -8 divided by 2, that's -4. Positive divided by negative or negative divided by positive, if you have different signs, it's always negative. That's not where you take like what's bigger or what do you have more of. It's just negative. Then we add 1. Different signs here. The difference is 3. I have more negatives, -3. So if you did not get -3, take a second and you might want to copy that math down so that you have an example. And then the last one, 100 divided by 2 is 50. 50 plus 1 is 51. All right. Okay, so I'm going to have you guys attach that to your lesson 1 page from yesterday. It's up to you, like how you want to glue it in. I would say you could just like glue it on the back of yesterday's stuff. So yesterday you had, oh, actually, you know what? I take it back. I'm going to have you guys glue it to this page. Just kind of fold and glue. I'll send glue sticks back in a second. So just kind of fold it and get it glued down there. Now there were a little bit of notes from yesterday, but we're actually we'll put them on today's page. That was what we did while you guys were working yesterday. Remember while people were, you were. If you were absent, that's okay. Just make a page called Unit 5, Lesson 1. And then glue this guy down. Oh, thank you, Miss LeMay. She's getting glue sticks. So get that attached and then take a look at your packet. Go to lesson 2. Go to lesson 2 in your packet. Thank you, Ms. LeMay. All right. Yeah. They might be jillions of Band-Aids, so that's what happens.
I'm sorry.
Oh, I'm not offended. I agree, 100%.
Like when they don't think that it'll keep on.
It's like the tissue. It's horrible. We go through like so much. All right, so get that glued down. Like I said, there were a little bit of notes we didn't get a chance to take, but we will put that in today's work. All right, so set this to the side, and you're looking at lesson 2 in your packet. Excuse me. All right, so lesson 2, we are continuing to work with our function machines, our function rules, but to start, we have a little activity that's going to bring up some review, like usual. So our lesson is Introduction to Functions. Our first activity is called Square Me. Bless you. Here are some numbers in a list. How many different numbers are in this list? So take a second and determine how many different numbers do we have listed here. So how many different numbers? Hopefully you got 7. So 1, 2, 3, 4, 5, 6, 7. They are all different. I do have some fractions. I do have a decimal. -3 and +3, although the digits are the same, the numbers are actually different. The value is not the same. Okay, so you could have equivalent numbers up here and we wouldn't count them twice, but we have to count the 3 and the -3 separately because one's positive, one's negative. Okay, if you have -3 in your bank account and I have 3, we are not in the same financial situation, right? You're about to get some overdraft fees and I'm not. Okay. Number 2, make a new list containing the square of all these numbers. So we are going to square these numbers. Does anybody remember from 7th grade what it means to square something? Or anything at all about squaring? Multiply a number by itself. Exponents. Okay, so squared might include an exponent of 2, right? If you guys remember looking at area, feet squared, right? Does that sound familiar? Like when you guys did the area and perimeter on Monday, there might have been something about feet squared or inches squared. So squaring involves a number times itself. It involves exponents. You don't need to write this down, you can just kind of look, but what happens and where that word comes from is from an actual square. I know this isn't exactly a square, but just pretend that's a square. If I had a square and this side was a length of 3, every side would have to be a length of 3, right? What would the area of this square be? Area would be 9, right? Not the perimeter, the area. The areas are length times width, right? So you could say that if I squared the number 3, it's 9, because 3 times 3 is 9. So that's kind of where squaring comes from, is from when we have a square, the area of the square is the side times itself. Okay, so side length times itself equals the area. So 3 times 3 equals 9. That's squaring a number. As for exponents, another way you might see this written would be like this. 3 squared. This tells me I have the number 3 and it's going to be multiplied by itself twice. 3 times 3. You might have learned in 7th grade, it's like repeated multiplication. 3 to the 4th power would be 3 times 3 times 3 times 3. Is that ringing a bell a little bit from 7th? Maybe. It was a while ago. It would have been like last year around this time or sooner. Right, so this is what we mean by square. We're going to take the number that we're given and multiply it by itself. Okay, so make a new list containing the squares of the numbers. Let me pull this here. So we're going to start with our first number 1. 1 times 1 is 1, right? So go through and multiply every number by itself. 3 times -3 is +9. When you're multiplying a negative times a negative, it always equals a positive. So take a minute. I'm going to do it up here. But at your desks, take each of these numbers in the list, and we're going to square them or multiply them by themselves. And then compare to what I have up here. Okay, so check yours to what I have up here. And then we're going to create a new list. Okay, so check to see that you got everything multiplied correctly, and I have a new list up there. All right, good. Everybody good with the list? All right. Good. So now number 3 says, how many different numbers are in the new list? Okay, so this is our new list. How many different numbers do we have now? Or how many unique numbers do we have? I heard a 5, I heard 6. Okay, so it is either 5 or 6. Now, when we say the same, or we want different numbers, we're talking about like the value of the number. Okay, so even if it doesn't look exactly the same, are we still talking about the same amount? Okay, so thinking about that, is it 5 or is it 6? Okay, well, we definitely, is there anything else that's a value of 1 in my list? No. What about 9? Yes, so we have a 9 here and another 9 here, right? How about a 4th? Is there another number that's worth a 4th? 0.25. Even though they look different, that's still the same number, isn't it? If I have a 4th of something and you have 0.25 of something, we have the same amount, don't we? If I have a 1/4 of a dollar, I have a quarter. 0.25 is a quarter. So these technically, even though they're written differently, they are equivalent. It's the same number. Okay. I don't have any other 4s or anything equivalent to 4, and there's nothing else equivalent to 1/16. So technically I have 1, 2, 3, that's a repeat, 4, 5 of the same number. So I have 5 different numbers. Now, anybody that thought 6, it's probably because of the 4th and the 0.25, right? So that might have just been the way it was worded, made it a little bit trickier. So number 4 says, explain why the two lists don't have the same number of different numbers. Okay, so what's happening is our first list, we had 7 numbers, 7 different numbers. All we did was square the numbers. How come I ended up with 2 repeats? That's what we're trying to figure out in number 4. So how come if I started with different numbers? Why would I have some things repeated? Why wouldn't I have 7 different answers? What happened with our math that made us have some repeated numbers after I squared? So take a second and look at your math and look at the numbers that repeated and see if you can figure out, how did we end up with the same exact number? 2 times, right? We ended up with the same number when we did our 3s here. We ended up with the same number when we multiplied -1/2, -1/2, and +0.5, +0.5. Yes. Yep, that's exactly right. When you have a negative times a negative, it equals a positive. So whether I start with a positive or a negative, when you multiply it by itself, you're going to get a positive number, right? And so since I have -3 times -3, I'm going to get the same answer as a +3 times +3, because a negative times a negative equals a positive. So that created a situation where some of my numbers ended up repeating. All right, so the two lists don't have the same number of different numbers because a negative number times a negative number equals a positive number. And that's something that we have to remember if you don't already know that by heart. That's what happened, because when I square a number, I'm multiplying it by itself. So if I start with a negative, it's going to be multiplied by itself, which is a negative. Squared numbers are always positive. So when you square a number, you always get positives. Okay. All right, next page. So yesterday, we were given inputs, we were given rules, and we had to figure out the output. Okay. On this activity, we're given the input and we're given the output, and we have to figure out, is there a rule? Will the rule work every time? Because like we noticed yesterday on those function machines, as long as the input and the rule always created a predictable output, you knew it was a function. So kind of like the one where you entered an A and it gave you a name that started with A, but they were all different names. That was not a function because we couldn't reasonably predict the answer. So if we have a number, can we figure out the height in inches? And is the rule that we can come up with a rule that would work no matter what we're given? Okay, so if we look at number 1, it says a person is 5.5 feet tall. Do you know their height in inches? Okay, so if you think back to 7th grade when you did converting with measurement, if you're given the number of feet and you know how the conversion is, could you figure out the inches? Yes. Okay. Does anybody remember how to convert feet to inches? What do you do to the feet? Shibli? Yes. Each foot is 12 inches. So if I take my feet and I multiply by 12 inches, I get my inches, right? Will that work every time? So no matter how many feet I give you, if you multiply it by 12, would you get a correct amount of inches? As long as you multiply correctly, right? So as long as your math is right, that would be a function, because whatever amount of feet I give you, you could complete a rule and get a correct output. So this is going to be a function. We're going to draw a little machine. So if you have 5.5 feet, draw a little arrow. We're going to write the rule and put it in a box like our input machines. So we know that if you take the feet and you times by 12, you get the inches. So we're going to say input times 12. And the reason I didn't write 5.5 is because I want to write just a general rule. So input times 12. And if we multiply 5.5 times 12, you get 66 inches. Every period I've had somebody feel like it was 65. Be careful with something like this. That 0.5 does not mean 5 inches. It means half of a foot. Half of a foot is 6 inches. Right? So 5 feet is 60 inches. Half a foot is 6. So 66 inches. And a calculator, 55 times 12 is 66. Okay, so this is a function because no matter how many feet you give me, as long as I multiply it by 12, I will get a correct amount of inches. And it'll work every time. It's predictable. There won't be a time where it doesn't work, that kind of a thing. Okay, next one. So part of this activity was to decide if it was a function. All the ones that we do are going to be functions. So let's look at number 2. A number is 5. Do you know its square? So we're going to be squaring the number. Okay, so if our input is 5, do you know its square? So that's telling me the rule that has to happen. I have to square this number. Okay, and if you remember from our warm-up, squaring means to multiply it by itself, right? So we're going to take the input and it's going to be multiplied by itself. But to make the rule look nice and pretty, we're going to write a little exponent of 2. Input squared. And if you're unsure about that, that means input times input. That's going to come in handy when we get down to number 4. Input squared means input times input. So if I take my input as 5 and I multiply it by itself, what do we get? 25. And if we look at this, it will work every time. As long as you're given a number, you put it in the machine, you square it, you're going to get the squared version. Like if we took all of those warm-up numbers in the list and we put them in our machine, we would get what you guys all got in number, I think it was number 3 on the 2 on the other side. All right, next one. The square of a number is 16. Okay, so on number 2, we took a number and we squared it. On number 3, we're going to be finding the square. So it's like we're undoing what we did in number 2. So number 3 is like backwards. So if I was using the same numbers for 2 that I was on 3, my input would be 25 and my output would be 5. So you don't write this down, but just so you know, it's giving you a number and it wants to know the square of 25 is 5. What would the rule have to be? Okay, so that's kind of what we're figuring out here, but it's with 16. Okay, so if for this, I'm going to multiply the input by itself. If I'm going in the opposite direction, I want to figure out, well, what times itself equals 25? What times itself equals 25? 5, right? So if I say there's a number, and when you times it by itself, it equals 25. Hopefully you think 5. 5 times itself, right? 5 times itself is 25. The only thing is we need to know, how do we write that? Does anybody remember what it's called, or how to write something when we undo a squared number? So there's a notation, or there are words that we can use to describe what happens when you have to think what times itself equaled that number. Anybody remember? Okay. So if I come back to this, I know that 5 times 5 is 25, right? Another way I could say this was the blank blank of 25 is 5. Back to 7th grade.
Square root.
Ah, thank you. The square root. Do those 2 words ring a bell?
We didn't learn that.
Square root. If you didn't, if you don't feel like you did, it was either a long time ago, like it was like the beginning of 7th grade, or you might have been absent, might have been sleepy, you might have decided that you were all good without the info. But square root is a decent part of 7th grade. You might have seen a symbol that looks like that. Does that look familiar?
We did it in this class. Remember when we did the paper? Oh, so that's simple.
Oh, did we do that in our first in lesson 1?
It wasn't a lesson. It was like a. I think like an example from second day of school.
Oh, there might have been one of our like first week of school activities, the 100 numbers or something maybe,
Yeah.
or the thing up on the wall.
Yeah.
Some of you guys might have done that. Okay, all right, very nice, good memory. So this symbol right here is called a radical. That's a square root symbol. Okay, so when we undo squaring a number, that's called square root. Another way to think about it, when it says the square of a number is 16, you could say, okay, I have a square and the area is 16. What would the side lengths have to be? Side lengths would have to be 4, right? Because 4 times 4 is 16. Okay, so bringing up square root. So for me to figure out that the square of the number 16, I need to figure out that number, we're going to square root. So we're going to draw our little rectangle. We're going to draw this, it's like a check mark and a division sign. Mash up. Square root of the input, yes. Nope, not plus itself, times itself. What times itself is 16? 4. Just like this, right? If you had a square, then the area was 16. Now, the thing to know is with these squares, especially this one here where we're kind of going in the opposite direction, there isn't necessarily like a trick or a way to be able to get the answers like this unless you memorize perfect squares. They're called perfect squares because a number times itself equals that. On a multiplication chart, it's diagonal down the multiplication chart. I'll show you guys in the next couple lessons as we need it, but memorization is really the best way to know these squares, and you're going to need to know the squares. So we'll start practicing those this week. Okay, memorizing those are going to be very, very helpful because the only way to do this would be to go through numbers in your head and multiplication facts till you figure out what times itself is 16. Your calculators have a little button too, if you notice on your calculator. Did you guys see it? It's right here. So on your calculator, if you type 16 and then click this little radical button, you'll get 4. Oops, if you could see the calculator. So if we say 16 and then we push this little button, you get 4. Okay, so that's how you can use the calculator for that. All right, last one. This one is going to require a little bit of brain power, and I'm going to need you to hang with me because it takes a minute to get through. But do know that even though this one might be a little bit tricky to kind of keep track of everything, if you think this one's difficult, doesn't mean that the rest of the lesson or the rest of the days are going to be difficult. Okay, with this, we take perimeter and area and like crash course and kind of smush it all up together. So just stick with me. A square has a perimeter of 12 centimeters. Do you know the area? So if you are given the information that you have a square, and if you're given the perimeter, could you figure out what the area was of that shape? Okay, so that's what we're trying to see here. Can we come up with a rule to figure out the area if we know the perimeter? All right, so off to the side, we're going to draw ourselves a little square. So draw yourself a square. And we know that the perimeter, and we're not really going to do anything below this, so you can write below. I know, or above, the perimeter has to equal 12. I know that. I know I have a square. I know the perimeter is 12. What would the side lengths have to be to make the perimeter 12? So that's the first thing we have to figure out. What are the side lengths, Daisy? 3? What do you guys think? If the side lengths are 3, the perimeter is going to be 12, right? How did you know it was 3? There are 4 equal sides, so you divide 12 by 4, right? So I have 4 equal sides, so I divided the perimeter by 4. So if you divide the perimeter by 4, you get 3. So that means that all of my sides are 3. Right? So that 4 happened because I have 4 equal sides. Right? Okay. So that's the first part, because for us to be able to figure out the area, we need to know how long the sides are. Right? So I use the perimeter to figure out how long each side is, and then I use those side lengths to figure out the area. Okay? So my perimeter is 12. I divide it by 4 because I have 4 equal sides. So that tells me that 3 is each side length. What do I do with the 3 to figure out the area? Times by itself, right? So I have to take 3 and I have to times it by itself to get my area, which is going to be 9. And label that area. So this is like the first part of what I had to do, right? So I had to take the perimeter. I divided by 4 because I have 4 equal sides, and I got 3, which is the length of each side. Then I take that 3 and I times it by itself to get the area. Okay, so I'm just making some little notes as to the math that we did, and the reason I'm doing that is because we have to come up with a rule. And we have to come up with a rule so that I could give you any perimeter and you could apply the rule and figure out the area. Okay. And we can't write like a novel. I can't say, well, first you take the perimeter, then you divide by 4, and then you take that answer and times it by itself. Okay, we're not writing novels. We need to make it like a quick rule. Okay, so we can start out our rule by taking the perimeter and divide by 4. Every time we have a square, we can divide it by 4 to find the side lengths, right? So for our rule over here, and I'll go back and forth. For our rule, we take our perimeter, or our 12, and I'm not going to draw the rectangle just yet because you don't know how much space you're going to need. So I'm going to take that input, right? So this is my input. It's not always going to be 12. I might give you the number 16, and then you have to figure it out, right? So you take the input, and we divide by 4, right? So we're going to write input divided by 4 for the 4 sides of our square. Now the trick comes in to where when you get the answer to that, you have to multiply it by itself. So to find a way to write that, you could say, then multiply the answer by itself, but that's a lot of words. On our previous problems here or on the front, what did we call it when you multiplied a number by itself? What was like the mathematical way to say that? I'm hearing, no, not square root, squared. I heard a couple people like whisper it, squared, right? So if I square a number, that's multiplying by itself, right? Up here, do you know it's squared? To find the square, it was input times input, or input squared, right? On this side, they said, make a new list containing all the squares, and we took the number times itself. So we can think of that word squared. So we could say input divided by 4, then square it. You could say that. Or we can put it in parentheses because this has to be done first. And I can put a little exponent of 2. That's a shorthand way of saying squared. So you could say input divide by 4, then square the answer, or then square the number. Or you could put it in parentheses and square it. And the reason we do parentheses is because the order of operations, we need to make sure that we take our perimeter divide by 4 first. So I put it in parentheses, that gets done first. If I didn't, I would have to do the exponent part first. And our output is going to be the area, which is 9. And if we think about it, if I were to imagine using the 12 here, 12 divided by 4, I do that first, it's in parentheses, I get 3. 3 squared, or 3 times 3, is 9. So this is a really quick and easy way to do all that work that we did over here. Input divide by 4, take the answer and square it. Okay, all right, turn the page. If we get time later, we'll come back to the other ones because they are good. Okay, the next part has the same exact scenarios that we just did, except there's something different we're going to do. We are going to start coming up with some vocabulary and using some of the mathematical words for functions. Okay, so all 4 of these functions that we worked with, we know they're functions because we could create a rule and the rule would work every single time. Okay, but what we want to start looking at is, if you look at the examples that they have written, it says, like on the second line, the height of a rubber ball, or the height a rubber ball bounces depends on the height it was dropped from. The day of the week does not determine the temperature that day. So there are situations where we want to write how something depends on something else, or what determines something else, okay? Because that's going to help us to decide what's a function or not. So if you don't need to turn your paper over, but if I look at number 1, and we try to think of this in terms of like what depends on what, or our answer. My answer is 66 inches. So if I came to you and I was like, all right, so there's a math problem and the answer is 66. What did I start with? I could have started with a million different things, right? So if I say the answer is 66, what did you start with? You'd have to say, well, what math did you do? What was the rule, right? So if my output is 66, you would have to either know the rule or you would have to know the input, right? If you don't know the rule, you can't figure it out. If you don't know the input, you can't figure it out. That's what we've been doing, right? So the answer, my 66 inches, depends on what my input is. Okay, so my answer here depends on what the feet were. The only way to get 66 inches is if I have 5.5 feet. So for number one, we're going to say that in this situation, when we have a person is 5.5 feet tall, do you know the height? Well, we could know the height, but the height depends on how many inches we started with, right? So the height depends on the height, I should say the height in inches. Hopefully you can squeeze that in. The height in inches depends on the feet. The height in inches depends on the feet. As the feet change, the height in inches is going to change, right? So if I have to find out how tall somebody is in inches, I have to know how many feet he is, okay? So if you have a bunch of people that you're measuring and we all know, all we have are rulers that measure feet, and I say, how many feet is that guy? You might have to say, oh, well, how many inches did he start with? Or, maybe whatever we're measuring with only has inches. And I say, how many feet is this guy's height? You say, well, how many inches was it? And then we can convert to the feet, okay? So the next one, the number is 5. Do you know it's square? Right? The only way I can figure out the square is if I know what my original number is. Okay, so the square depends on the original number, right? So the square depends on the original number. So we're just kind of rewriting these, talking about like what depends on what. And if you notice so far, the height was what we were looking for. What we were looking for depends on what we started with. What we were looking for, we're looking for the square here. What we're looking for depends on what we started with. So the next one, the square of a number is 16. Do you know the number? So this number depends on what the square was. The number depends on this original, right? I don't want to write on the original though. I want to rewrite that as something else. So instead of saying the original number or the number depends on the square of the number, or that's a lot of words. Don't turn your paper over, I will. On number 3, we're saying this number depends on this one, right? So this number here depends on this number here. We said that before too. 25 depends on what 5 is. 66 depends on what this is. This number is our output, right? What's this number? What like math word have we been using for this original number? Every time our original number is called the what? The input. Every time our original number has been the input, right? So in this case, my final number depends on what the input number is. So instead of saying the original number, I'm going to call it the input. Is that okay? I'm just trying to save us some pencil. So the number that we get depends on what the input was. So if I say, what's the answer going to be? What's the output going to be? Well, it depends on what you put into the machine, right? Say, okay, we're gonna run this machine again. What's our answer gonna be? Well, it depends on what you put into the machine, right? So the number that I get depends on what I put in. Our last one. The square has a perimeter of 12 centimeters. Do you know the area? Yes, I can figure out what the area is, but I can only figure out the area if I know the original piece of information, which was the perimeter, right? So area depends on the perimeter. So the area depends on the perimeter. Now, if we wanted to kind of come up with a general way to kind of look at each of these, if we think about it, for our first one, the height in inches was the answer, right, or the output. The feet was the input, right? On number 2, you can leave yours on the side that you're on. The output, or 25, right? So the square depends on the original. The square depends on the original. The number depends on the input. The area depends on the perimeter. So every time, didn't our output depend on what the input was? So we're gonna make a little note over here that says, I don't know, pick a place. The output depends on the input. So make a little note that says the output depends on the input. Which makes sense, right? If you want to know what the answer is, well, that depends on what the question was, right? Okay, and we're going to talk a lot more about that tomorrow. So if that's a little bit like you're not sure what just happened, that's okay. We're going to talk more tomorrow. Last part. It's a quick one. Next part, 2.4, same function, different rule. Which input-output rules could describe the same function, if any? Be prepared to explain your reasoning. Okay, so we're going to look at these different rules, and we're going to see which of these functions are actually talking about the same thing. Okay, so let's look at the first one. Our input is 7, and we're going to square it and get 49. If you remember what squaring it means it's going to multiply by itself. So that means I would take 7, which is my input, times itself, and that equals 49, right? So we're just kind of putting a little bit of math to what happened with our rule, because we need to figure out what of these functions are the same and which are different. So the next one, find the area given the side length. Now, area can be found with all different kinds of shapes, but it's always length times width when it's a four-sided figure. We don't even know if it's a four-sided figure or if it's a triangle or what, but we do have an input and an output. So if my input is 10 and my output is 100, what can we figure probably was happening? What area were we finding?
The area of the square.
Area of a square? What do you guys think? If my input is 10 and I'm having to find the area, this is the side length. That's if it's only giving me 1, that must be the only side length, right? So if my side length was 10 and my area was 100, I would have to have done 10 times 10. It must have been a square, right? Has to have been a square. And I get 100. Now, if you look, we actually did the same exact math as we did above. Got different numbers. But if you look at the next machine here, I have the same input and the same exact output. So if we look at the rule, is this the same rule as we had above where we were going to multiply by itself? What did you add? 10 plus 90. According to this, our rule is 10 plus 90. That also gets us 100. However, these are different functions because the rule is different. These are the same function because the rule is the same. So off to the side here, you're gonna make a note that says these are the same function because they have the same rule. Even though the rule is written differently, it is the same rule. We're almost done. There's still one more thing. I know. I'm making you guys work today. In your math notebook, a couple things you're gonna write down. We didn't get to do it yesterday. I know we're slipping. All my other classes are getting these parts done. We're usually like ahead of everybody else. It's not your fault. I'm taking the time. Okay, so open your math notebooks and we're gonna copy a couple things down. I'm gonna put together yesterday and today into a quick short summary for you. Okay, so title your page, Unit 5, Lesson 1 and 2. Unit 5, Lesson 1 and 2. And we're gonna say input. Draw a little machine here. Input, rule, output. So that's our little function machine. I need you to stop talking, please. Got stuff to write down. Okay, so we do know that we take an input, apply a rule, get an output, right? We learned today that different rules can actually represent, bless you, the same function. Okay, so we just saw that different rules can actually represent the same function. So saying that we square a number and saying that we're going to find the area of a square is a different rule the way it's written, but it's actually the same. We have also learned that the output depends on the input. And that's it. Scribble that down and you're done.
No, I remember something. Can you pull them out?
Give me a second. That's it, you guys. Pack up good. Now we can say good job, class. Good job, class.